Okay, let's move on to deep residual learning, basically ResNet. I'm sure you have heard of it, but let's go a little bit deeper into why they are important. So the idea is that they want it to go as deep as possible. So as you see, there is a trend here. So the deeper, the better. The papers that we are reading, they're just trying to make their neural network deeper. And something weird was happening. You expect, as you make your neural network deeper, for it to have a higher capacity because you have more parameters. And at the same time, it has a bigger receptive field. It's looking at a larger patch of your input image. So it's looking wider. So you expect your neural network to learn better as you make it deeper because it has more parameters, it has more capacity. But in practice, once you sit behind the computer and implement it, and let's say you come up with two neural networks, one is 18 layer deep and the other one is 34 layer deep. The 18 layer is training like this. That's the training step. Whenever you have a drop in your loss function, in your error rate, in your loss function and your error rate, that corresponds to learning rate decay. So if you remember, if you're using a stochastic gradient descent, you have a learning rate. And let's say at this point, your learning rate is 10 to the power -2. And then you suddenly drop it to 10 to the power -3. It means that you are now focusing on during your optimization, you're focusing around your local minima that you found or you're trying to find. And there is another drop here in the accuracy.
That's interesting and counterintuitive to me. It would seem like when your learning rate decreases, your change in percent error then would slow down as well.
And it's sort of doing, if you see, there is a first drop, and then here the change is slower compared to the change here.
Fair enough, yeah.
But then initially, this is external to your system, you suddenly drop your learning rate. So it's gonna start focusing on your local minima really fast, there is a huge drop, and then it's gonna oscillate slowly. Same thing here.
Yeah, that makes sense then.
But it's the same behavior for both of the networks. One of them has less capacity compared to the other one. You would expect these two curves to be switched. You would expect the one that has a higher capacity to give you lower errors. But then it's weird. As you made your neural network more powerful, the error went up. It means that your neural network is making more errors. It's identifying more cats as dogs. Okay, it's making more errors. So you might think that you're increasing the capacity, but then why is this happening? It's contradiction. The reason could be either two things. It's either your neural network not training properly or something weird happening with your gradients. So let's investigate that. So to fix that, this paper, which is a huge paper in deep learning, if you look at the number of citations, it's crazy. So it has a huge influence on many other works. They say that maybe there is a way for the network to ignore some of the layers if it doesn't have to work with them. That's why they add a shortcut connection from one layer to the other one. And what the network does, if it's too complicated for the weights to go through these layers, it's just gonna ignore that. And it's just gonna go through the shortcut. It means that you're ignoring one of your layers. Your network might be 34 layers deep, but then it has a bunch of shortcuts. And if it has to go through these complicated nonlinearities, then it will. If it doesn't have to, it's gonna go through the shortcut and ignore that layer. And basically maybe your plain 34 layer deep neural network is gonna end up being 7 layers deep once the optimization is done. Or initially during training. Maybe it starts with going through the shortcuts most of the time. And then as it needs to focus on more complicated examples, then it's going to go through the more complicated part of the neural network.
Is there a parameter that controls if it goes through the shortcut?
There are some other works that do that, but this work doesn't. It's just you add your input to whatever your neural network is telling you on this block of your neural network. Okay, what I'm explaining here is a block of the neural network. It's just, think of Lego puzzles. It's just one of the blocks.
So
then end up using this.
In this work, it's always going to go on both paths and then just combine the result. It's not going to choose between them.
No, it's going to go through both of them. But then if the weights are 0, and initially we are going to initialize them to be very close to 0. Do you remember the initialization from last session? So it's most of the time around 0. So the initialization one is square root of the standard deviation of the initialization was square root of 2 over n. And n was related to your filter size and the number of input channels. And the number of input channels is usually, I don't know, 256. And let's say your kernel is 3 by 3, it's 256 by 9. So that's a big number. Square root of 2 over a big number, it's going to be a small number for your variance of your initialization. Okay? So initially, the network is going to go most of the time through this route. Does that make sense?
Yeah, that makes sense.
Another interpretation is that it's easier to learn the difference between one layer and the other one compared to learning the entire thing. We are going to go through some super resolution paper later on. If you're super resolving your image, the low resolution image is already a good approximation of the high resolution one. Okay, think of this as the low resolution and the outcome as the high resolution. So the low resolution one is a good estimate of the high resolution, and the other way around also. So these are good estimates, but then you're learning only the difference. The neural network is doing the part of learning the difference. So in practice, these are not going to be too deep. These blocks here are going to be 2 layers deep. One convolution and then another convolution applied on a nonlinearity ReLU. The question is what happens if the input dimension is different from the output dimension? Then you cannot just add 2 things with different dimensions. And we know how to fix that. We use 1-by-1 convolutions. So is that clear? So 1-by-1 convolutions are useful for changing the dimensionality of your input and output.
So my question now is thinking about this. It makes sense so far. Is what about these maybe inputs, or what about the outputs of the layers makes it so that like you're saying, as the learning goes on, the weight layers become more important or larger. They're initialized to 0, then they grow later on. Like by what process or by what phenomena does that change happen? When is the identity the more important channel, and when is the f of x the more important channel?
So there is this loss function from the previous slide. You write that loss function, then each time an example goes in your neural network, your loss function is showing you how much error you made, okay? How much loss you had. Then you have to back propagate that loss to adjust these weights. So when the neural network is seeing that it's committing a lot of errors going through the identity path, then it is forced to go through this part of the more complicated part for the errors to go smaller. So it has to do with the way that training is done and backpropagation.
That's really interesting. Yeah, that's fascinating.
Wait, so WS is initialized to identity, and then it can be driven like away from identity, like in order to put more weight on the weighted layers?
So there are 2 scenarios that could happen. One is that X and Y have the same dimensions. If they have the same dimensions, this is what you use. So there are no weights on X. Okay, that's exactly what you use. You use an identity without any weights. But then the problem arises when you want to go, I don't know, from 256 dimensions to 512 dimensions for your output, then you cannot simply add them together, correct? That's when you introduce a one-by-one convolution or just a simple matrix vector multiplication to adjust the dimensions to go from 256 to 512.
And is that WS similar to like these like injection and projection matrices that you'll use in like multigrid? So it's not supposed to change any size. It's just trying to get like a one vector to become a one vector in a different dimensional space.
Yes, so these are just projections.
Got it. Okay.
Or expansions, depending on what they are doing.
And
Most
then,
of the time we're doing dimensionality reduction, but sometimes you want to expand.
There's no learned variable weighting in that though.
No, there is a weight variable.
Oh.
W is the weight. So there's a catch.
So at that point, it becomes almost like an Inception module in the sense where you have these different paths that you can take with different convolution layers in them, but just less complicated.
You are sort of correct. It's very similar to an Inception module. Yes, there is one by one convolution here, and then what you're doing is just concatenating the output of your block and X and then multiplying it by W. It's very similar, but there are some differences as well. But the main idea is this. This is the one that the paper is going to use. So we are going to try to avoid this. Can somebody tell me why?
Well, because then you still have to learn parameters for WS, right? And that's sort of getting away from the point of this.
That's one aspect, but then it's easy to learn from one layer to the other one because there is no nonlinearity. F is nonlinear, but this guy is linear. So learning that is easy, but what is the catch? What's the difference between this and the other one? It has more parameters. The one on top is not adding any parameters. So it's basically the same cost. If you take a VGG19, you're gonna end up with just one more addition per layer. So it's nothing in terms of cost. It's also nothing in terms of memory. So you're not adding more parameters to your network. But this one is adding more parameters to be learned. So that's the difference. That's exactly what the paper does. They take VGG19, and VGG19, we covered it. I think it was in our third slide. You take VGG19 and you modify it. And you're gonna get a 34-layer plain neural network, and that's what we had here. That's a 34-layer. Basically, what are the changes? You're changing these 3x3 convolutions, and you're replacing them by a single 7x7 convolution for your first layer. You're making it a little bit deeper. You're adding more layers. Same thing here, you're adding more layers. And then in the end, you have average pooling from network-in-network paper compared to fully connected ones. So that's the change you make. And then to make it a residual, you add these connections here, these shortcuts, the ones that we introduced up there, you add them here. Let's see if the dimensions match. This one is 64 dimensional. So you're adding a 64 dimensional to the output, which is 64 dimensional. So you're just adding, you're using this. Same thing here, but then let's take a look at here. The output is gonna be 64 dimensional, and then here, the output is 128 dimensional. So these dashed lines, these dashed curves is where you're actually using the second type of a connection. So same thing here, the dimension, wherever the dimensions don't match, you're using that. Or you can choose not to use that because there are only 3 of them. So probably they're not gonna make a huge difference. You can just drop them if you want. So what is the actual change? So I'm here. Now you reverse the pattern. Previously, your 18-layer deep neural network was doing better than your 34-layer. Now you change the pattern. Now things are working as you expected. Your 34-layer deep neural network is doing better than the 18-layer. So that was intuitive arguments, and this is actual empirical argument. that things are actually working. Any questions?
Why is this called deep residual learning then?
Why is it called deep residual? Deep is because it's deep. You have multiple function compositions on top of each other.
Mhm.
That's deep. And it's really deep. It's 34 layers deep. Why is it called residual? Because of these residual connections.
Got it.
The cool thing is that these residual ResNets, they don't have to be this deep. Basically, if they decide that they don't need this block, they're just going to ignore it and set the weights to 0 during training and go through these ones. Okay, and whenever you have a shortcut, it's basically avoiding that part of the network.
So is it essentially the same as like a hyperparameter for how many layers to have? You can train out some layers.
That's a cool way to think about it. Yes, sort of the network knows how deep it has to be. You make it as deep as you can fit on your GPU, and then you let the network decide how deep it wants to be. Clever way of doing it, yes.
Can you go in after the fact and sort of like prune the network in places where it's chosen the shortcut over those layers?
Yes, there is actually, we are going to cover that.
Okay.
When we go to small networks, so far the trend is we want to make our network as deep as possible, as wide as possible, to get more accurate and win ImageNet competition, to claim first position.
Whatever the cost, sort of.
Whatever the cost. Except for Inception modules, which are trying to sort of take into account the cost. But other than that, the general idea is we want our network to be as large as possible.
Okay.
But then when we go to make networks smaller, there are various ways of doing it. After the fact, during training, and so on. We're going to cover that. There is actually another contribution of this paper, and that's bottleneck. So rather than going from, if you are going from 256 dimensions to 256, then these convolutions are going to be huge. The cost is huge. And we saw this trick before. You use a one-by-one convolution. We saw it in Inception. Now we are seeing it here again. But now in the, including the ideas of residual connections. You first project from 256 dimensions to 64. Then this 3x3 convolution is going to be really cheap. You do that, and then you project back into 256, and then you add it. And they use a lot of bottleneck connections. For instance, this 256 here is just a bottleneck connection, and these are the actual networks. For 18 layer deep, 34 layer deep, 50 layer. For 50 layer deep, they're introducing these bottlenecks. Otherwise, the cost is a lot. They go up until 101. You hear these words a lot. ResNet 50, ResNet 101, and this is ResNet 152. It is 150 layers deep. And Brandon has a question. For those of you who have questions, you're more than welcome to ask. And for those of you who want to leave, you're more than welcome to leave. We are right on time. Brandon is saying, is there a certain minimum amount of data needed to utilize an ultra deep architecture? These are good questions, but these are theoretical questions, which I cannot answer. Usually the thing that happens is that somebody gives you a data, and then you have to live with that data. So the data set has this size, and then you have to make your best efforts to get the most out of your data. So usually the size of the data is given. But these are really good questions. I mean, you can investigate them. It could be the topic of somebody's dissertation or a PhD. Does that answer your question? Perfect. Any other questions?
So I've seen these sort of skip connections in things like UNet. Is it a similar idea there when you get into segmentation, that sort of information from previous layers is useful later on?
It is similar, but in UNet, we are going to cover that later on. The objective is slightly different. And in segmentation, the objective is different. Here you want to get a number out, a probability out, Over there, your probabilities are going to be pixel-wise when you do segmentation. And you do those shortcuts for different reasons. Over there, it's for you to get a better estimate for the boundaries of the objects. Here, the objective is different. Here, you want to go as deep as possible. And why do you want to go as deep as possible? Because the deeper you go, the more features you're learning, the more abstract features. Does that answer your question?
Yeah, cool. Thanks.
Yeah. Would there be an advantage of doing this over a depth of? That's a great question. There is actually a table in the paper studying whether you should have 2 of these or 3 of these or 1 of these. And then they are going to compare the learning rate, the errors, and they decide that no, it's not worth it to add more than 2. And that's why they stick with 2 of them. Any other questions? Can the depth be a variable, like 2 for certain layers and 3 for others? It could. But if you think about it, these are discrete variables, 2 versus 3. And then it's hard to optimize over them because then your gradients doesn't make any sense. And the other thing is, these are not learnable by your data. This has to be a mechanism outside of your learning process. You can think of these as hyperparameters. These are not parameters. The other problem is you're changing the structure. You need to write a different type of a neural network each time. And the computational graph is going to be different when you compile it. When you use TensorFlow to compile your neural network, then each time it has to either use 2 or 3. So there were a couple of problems. One is technical. How do you implement it? The other one is mathematical. How do you use gradient descent on discrete stuff? Does that answer your question? But we will see how to optimize over those sort of things, like 2 layers versus 3 layers. We're going to learn how to do that later on. When we do automatic machine learning, we're going to see that. Any other questions?